And when I simplify, that should just give me x squared plus 1 exponent 5/2. So later on, you're gonna see that I changed the absolute value around x squared plus 1 for parentheses. It's just because x squared plus 1, it's always positive, so it will not be a problem. So multiply both sides of the original differential equation by the integrating factor. I got x squared plus 1 exponent 5 over 2 parentheses y prime plus 5x over x squared plus 1 times y equals to x squared plus 1 exponent 5 over 2 times x over x squared plus 1. So we can see that the left side can be rewrite as the derivative of x squared plus 1 exponent 5/2 times y. So we have d over dx x squared plus 1 exponent 5 times y equals to x over x squared plus 1 times x squared plus 1 exponent 5/2. So we're gonna now integrate both sides with respect to x. Um, I realized after that I like kind of like skipped the steps. So when I integrate like the second part, which is x over x squared plus 1 times x squared plus 1 over 5 over 2 dx, I used u substitution. And so you can see that on the page, but last. So u is x squared plus 1. So du equals to 2x dx. And x dx equals to 1/2 du. So now we replace, we have 1/2 integral of u exponent 3/2 du. So when we integrate that, we have 1/2 times u exponent 5/2 times 2 over 5. That give, when we simplify by 2, and we have u exponent 5 over 2, everything divided by 5. So now we replace u by its value, which was x squared plus 1. So when I integrate x over x squared plus 1 times x squared plus 1 exponent 5/2, which I also transform, I end up with x squared plus 1 exponent 5/2 over 5 plus c. So now I have y a factor by x squared plus 1 exponent 5/2 equals to x squared plus 1 exponent 5/2 plus c over 5. I divide both I divide the by both side by x squared plus 1 exponent 5/2. So I end up with y equals to x squared plus 1 exponent 5/2 plus c. Everything divided by 5 times x squared plus 1 exponent 5/2. So now that can be considered as my general solution. So with the condition that I have y0 equals to 2, I replace x and y by their respective values. So 2 equals to 0 square plus 1 exponent 5/2 plus c over 5 times 0 exponent 2 plus 1 exponent 5/2. So we're gonna solve for c. I do cross multiplication. So 2 times 5, 10 equals to 1 plus c. Then c is equals to 9. So that gives us our final answer, which is y equals to x squared plus 1 exponent 5/2 plus 9 divided by 5 times x squared plus 1 exponent 5/2, or y equals to 9 over 5 x squared plus 1 exponent 5/2 plus 1 over 5.
All right, nice. Okay, thank you, Liz.
Thank you.
Very thorough. GE6, 人数先 4.
Okay, so I'm presenting the homework 3, number 6, which is given the equation is xy prime plus 4y equal to, what did I do? Oh yes, is equal to e to the negative x over x to the cube. And the y of 1 equals to 0, where the x is greater than 0, which is positive. So I just follow the step that is in the class. It says so I have to isolate the y prime by itself. So I divide the x on both sides. So I got a y prime plus 4 over x y equals to e to the x and over x to the fourth. And then do the rho of x go to the e to the integral 4 1 over x dx, which is equal to x to the fourth.
Hold on 1 second. Do not
Yes.
just read what you wrote. Explain what's going on. Explain, what are you doing, why you do what you're doing. Okay, don't only read. Explain to us what are you trying to do first, okay?
Like integrating factor? Is that called?
Exactly. Right, you're calculating integrating factor. Great. Yes, use it.
So okay, thank you. So it's the rho of x, which is equal to x to the fourth, and then I multiply the differential equations by the rho of x, which is give out like x to the fourth times y prime plus 4 times x to the cube y equals to e to the negative x. Then I take the derivative of given the notice about like d of over dx rho of x times y, which is equal to the px and qx, which is the equation above, x to the fourth times y prime plus 4x to the cube times y equal to e to the negative x. So the rho x times y, which is x to the fourth times y, equal to the integral of e to the negative x dx. Then I integrate out, so it is equal to negative e to the negative x plus c. Then divide both sides with x to the fourth, which I got y equal to 1 over x to the fourth times the negative e to the negative x plus c. And then next step, I have to find out the c. So I plug in the number, which is the x equal to 1 and the y is equal to 0. So I got the equation as 0 equal to 1 over 1 to the fourth times the e to the negative 1 plus c. And then the c will be equal to the e to the negative 1. So the particular equation is y equal to 1 to the x to the 1 over x to the fourth times negative e to the negative x plus e to the negative 1.
All right.
Thank you.
Thank you. So this is Junyi, Shuxian, number 4. And I think that should be the last presentation. No, that's not true. The last one will be Ryan. Ryan is going to talk about a new one, a new lesson. Shuxian, are you here?
Yeah, I'm here. I think
it's your turn.
I waiting for somebody else, right?
No, it's your turn now.
Oh, okay. Let me see. Share. Oh, I cannot find it. So
Then you can present next class. So we'll have Ryan to present then.
okay. All right.
All
Okay.
right. Okay. Thank you. So Ryan, your turn now. Try to explain to us what is it before you explain your work. All right. So teach us. Basically, teach us first.
I'll try my best, but I'm not too good with proofs. So
Then use your homework. Use your presentation as an
of
example.
course.
Okay.
But I'll try my best to kind of explain what's going on.
Okay. Thanks.
So I mean, as we've all probably noticed, we can't just magically solve every differential equation. It's basically does it fit this pattern? Does it look like this? Then we can use this method or this technique. So in this case, the form we're looking for is one function dx plus another function dy, or we could also have dy over dx alternatively, because if you just do algebraic rearrangement, you'll notice that those are basically the exact same. Like for instance, I took this, moved it to the other side, divided by dx, moved it back, and there we go. Now we have this form. So what we're looking for is something in that format. And in order to do this particular technique, we have to check if it's something called exact. And so what we do is we basically take what's in front of the dx or what's on its own, and we declare that as m, or you can call that whatever you want, but it's basically a function of typically x and y. And we do the same for what's in front of the dy or dy over dx, and we call that n. Now, what we then do is we do a partial derivative. Now, I know some people here didn't take Calc 3. The gist of a partial derivative is basically you treat everything that you're not differentiating as a constant. So I'll go into a bit more detail. What we want to do is for m, so that's the first one, with dx, we want to partially derive that in terms of y. So I have 2x squared here. I'm going to treat that as 1. It's a constant. The derivative of 1 is 0. And now I have minus 3y squared. Derivative of that is negative 6y. So I discard the constant, which is x, and I leave the y. And so my partial derivative in terms of y is negative 6y. Now for n, as you can see, I've got y squared. That obviously becomes, I'm sorry, I'm deriving in terms of x. So I'll change what I'm saying a bit. And notice that what's in front of the y gets derived in terms of x. So y squared is a constant in term when we partially derive. So it's just 1. Derivative of 1 is 0. And now we have minus 6xy. Well, we basically in our heads set y to 1, and the derivative of x is just 1. So what are we left with? We're left with negative 6y. And therefore, our partial derivative in terms of x is negative 6y. And as you can see, these are both equal to each other, which basically means that we can solve this differential equation using this particular method. hopefully. And so what we're looking for, and that's kind of the definition of exact, we're looking for a single function in terms of x and y, which has a partial derivative in terms of x, which is equal to 2x squared minus 3y squared. So if you notice, that's our first term. And then it has a partial y derivative of our second term. And so basically, to check if it's exact, you swap the x and y to partially derive. And then for this method, you go back to dx, dy. So what do? We say f of x comma y equals the integral of f, the partial derivative of f in terms of x, dx, and that's equal to the integral of 2x squared minus 3y squared. Again, my first term. Now you can actually do this the other way. You're going to do the integral of f sub y dy equals the second term dy. And so taking the derivative, or I'm sorry, taking the integral, we get this. And basically what happens is, since we are taking the integral of a partial derivative, instead of assuming we lost a constant, we're instead assuming we lost a function. Because as you saw up here, my y squared just vanished. And that's because we set it to a constant. So we're now assuming that we lost an entire function in terms of y. And so we have the integral plus our constant, which is now a function in terms of y. Now what we do is we take the partial derivative in terms of y of the of what we just got here. And again, this goes bye-bye. And negative 3xy squared becomes negative 6xy, plus we can take g of y, derive it in terms of y, and get g prime of y. And so now we have fy equals this, and we have fy equals this. And so we set them equal to each other, and we solve for g prime of y, which in this case ends up being y squared, because negative 6xy cancels out from both sides. We then integrate both sides, and we get our g of y plus a constant equals the integral of the other side plus a constant. We turn both constants into just one, and we have our g of y. Now, I know it's a lot of steps, but we've got our g of y. We plug it back into here. We move the constant to the other side of the equal sign, and we have our f of x comma y equals this. Now, there isn't really an easy way to simplify that, so there's also not an easy way to check your answer, other than if you take the derivative of this in terms of x, it's going to be this. And if you take the derivative in terms of y, it's going to be this. And so those are the steps to follow. First you check if it's exact, then you integrate one of them. You make sure to keep that extra function that you lost, implicitly. Then you take the derivative of that in terms of the other variable, solve for that function, and then you're done.
Great. Great job, Ryan. So
Thank
from
you.
You're going to teach this class, okay? All right, let me ask a question.
Sure.
Let me ask, not for you. I'm asking
okay.
for the whole class. So
all right. Thank you.
If someone hasn't taken Cal 3, which is a vector calculus, write 1 in the chat. So let me know who hasn't taken Cal 3. okay, so all of us have taken Cal 3 vector calculus. That's great. Otherwise, it would be difficult because we're going to involve partial derivatives. Oh, so then you didn't take Zihao, or you're taking it right now. Suzanne, if you haven't taken Cal 3, I'm not sure if you are going to get this. Oh, they allow people to take this class without Cal 3. I didn't know that.
I'm taking it right now. I haven't
Oh, you're
taken it
taking it
before.
right now. Okay,
Yeah.
so that's fine. That if you're taking it right now, if you, I don't know, have you has the professor talking about partial derivatives yet? Because this involves partial derivatives.
Professor, is my turn now or what?
Oh, you found it?
I guess. Okay. I check in and then I use another thing so I can find. Let me try another way because last time I used my
Just make
email.
sure. Okay, just make sure you can present. Otherwise, you can present next class.
Oh,
You
this is not right.
you were successful. That's not yours. You were successful last class. So do the same thing. Go to share
Okay.
content.
So I did already. So
First open your homework on your screen. Then go to share content. Then choose share application / screen. Then pick the screen.
look, I need to download it now.
I don't know your computer, right? You need to open it first. Yeah. It shows up here.
You saw it? Oh, okay.
I saw part of it. I didn't see the whole thing.
I don't know how can I do now. Just part of them.
Well, if you click on it, you need to open this file on another screen on your computer.
I did already. Even though I save at the desktop, so but I cannot. I found it, but it cannot open it, so that's a problem.
It's possible for you to move your screen, the current screen, to the right-hand side, so you can show the whole homework.
Right-hand side.
Because I only see part of it.
Yeah, so that's why. So it's no good. So.
All right. So why don't you just make sure after class so you can present next class.
Sure, no problem. Okay.
All right. Thank you.
Thank you. Let me start it.
All right. So we're going to talk about exact equations today. Okay. Exact equations, as Ryan has mentioned over and over. And also some substitution methods. So, but this is our focus, all right? We're trying to solve this kind of equations. So let's read this. Sometimes we can take a substitution in differential equation that can transform the equation into one we know how to solve. Suppose we have such dy dx equals this. Okay. Suppose we have this dy dx equal to the little f of xy, okay, in terms of two variables. So for Zihao and Suzanne, you're taking it now. You're taking vector calculus now. You are dealing with vector. You're dealing with vector valued functions. You see this function? It's a function with two variables, and we call vector valued function. So let such variable v equals alpha of xy to get an equation in v and x instead of y and x that we can solve. So let's see this example. So dy dx equals to x plus y plus 3 squared. So what do? We use this trick, substitution trick. So we say, okay, let v be x plus y plus 3. Then in this case, we can single out y. So y is v minus x minus 3. Then dy dx, we take a derivative of this, dy in terms of x. This is dv over dx, right? V, take a derivative of v in terms of x, that's dv dx. So this is implicit differentiation, right? We're taking derivatives simultaneously. And the derivative of negative x is negative 1. Derivative of negative 3 is 0. So we get this differential equation. Now we substitute dy dx into the original equation we are given. Dy dx is given as this. So we substitute in dy dx. Well, what's this? Remember we named this v, right? So we have this v squared equals to dv over dx minus 1. So we have this v squared equals dv over dx minus 1. Then dv dx is equals to v squared plus 1. What's good about this? What's good about this? Now we can separate those two, right? Now we have dv over 1 plus v squared equals to dx, right? We have these separable equations. Then we can integrate both sides simultaneously. We integrate this, we integrate this. Integration of 1 over 1 plus v squared, if you remember, that's arctangent. That's arctangent plus a constant. Integrate 1, that's just x plus constant. So arctangent of v equals to x plus some constant, right? Then we know v is equal to tangent of x plus some constant. And the v we define as x plus y plus 3. So that means this one just equals to tangent of x plus some constant. And then y can be written as v tangent x plus some constant minus x minus 3. Marvelous, isn't it? Anyone has any questions?
Yeah, so like what are the, like when you're looking for a substitution, is the general rule just to swap in something for the entire side of the right equation?
Yeah, for this one, we'll see more example of this. All right.
Okay.
So this one works this way. This one works this way. So we'll let v be this. Then we rewrite v, because we want to solve v in the end. Right? We want to solve v in the end. So our goal is to find an equation to satisfy this differential equation. So remember, that's our goal. So in the end, we want to be able to write a y as a function of x. Or
Good evening.
Yo, good evening.
All right, guys, so we'll be teaching the class since the professor is having some trouble.
Wait, Professor, I have a question.
yes.
Oh, wait, sorry, no, sorry. No.
Oh, no
Yes,
problem.
He disappeared for a second.
Yes, we were very worried.
Oh, I disappeared?
Yes, you disappeared.
Oh, really?
Into
Yes,
the
of
void.
course.
Oh,
Yes,
I have
yes.
no idea.
Oh, well, it's okay. You can tell us again if you'd
It's
like.
all, oh, let me see.
Yeah, so like,
Oh,
what was the qualifications for a substitution? Like, how did you know that it was you're supposed to put in a V?
oh, okay. We'll get into that. Not to worry.
Okay.
Yeah, I see so many comments here now. Sorry, guys. I didn't know what's going on. I have no idea. On my side, everything's fine. Just all of a sudden, I receive all those comments. Okay. Okay, you see the miracle is what? After doing this substitution, the miracle is we simplified this complicated equation into something solvable, right? You see here, there's no way to do, so far we have learned separable, right? So we cannot separate x and y. We cannot put this equation as a separable equations. But somehow, when we use v to substitute, and then we get this, and then we can put as separable equations. Then the rest just use the technique of, you know, solve separable differential equations. All right, now let's see. In general, so to answer, I think that's David's question, right? Differential equations of this such form, dy dx equals to capital letter F of with some ax plus by plus c can be transformed into separable equations by making substitution of v equals to ax plus by plus c. David, does this answer your question? It's
Yep.
always good to have questions. All right,
It's
great,
crystal clear.
great. All right. Okay, that's for this family. So it's for this family, we can use substitution method. Okay, homogeneous equations. So little f of xy is a homogeneous function if f of tx comma ty equals to f of x and y. So what does this equation tell us? This equation tells us that's a ratio between x and y. So if you think about ratio of x to y, or x divided by y, or y divided by x, it's going to be the same as tx to ty, or tx divided by ty, or ty divided by tx. So that's some ratio. So in the function involves the ratio of x and y. So that's why when you multiply by a common factor, the function itself doesn't change. Let's see an example. So this function is homogeneous. Why? So we could substitute x with tx, y with ty, and we see it's the same as f of xy. So we go through the calculation, because t squared happens in the numerator, t squared happens in the denominator, so t squared is a common factor. T squared is a common factor. So the function doesn't change. So that's called homogeneous function. Another way of seeing this is we can write f of xy equals to some other function with a ratio of y to x. Let's see an example. So the same example, right? Is the same example? Yes, the same example. So x squared plus 2y squared, if that's because this y, because we can rewrite this, right? We can rewrite, we can think this, we can factor out x squared, rewrite x squared inside the parentheses as 1. Then, because we factor out x squared, so we have to have y squared divided by x squared. Right? Just rewriting. So we're trying to factor out x squared. Then x squared becomes 1. 2y squared becomes 2y squared divided by x squared. Same thing for the denominator. We factor out x squared. Then inside the parentheses, 3x squared becomes 3. Negative 5xy becomes negative 5y over x. Right? And then we see the common factor of x squared. X squared becomes 1. So we're left with 1 plus 2y over x squared. 3 minus 5 y over x. So this is another function with a variable of y over x. So if we let another variable, let's see v, actually this is read as new, but let's read as v, equals y over x, we see little f of xy can be written as capital letter F of v. This is 1 plus 2v squared divided by 3 minus 5v. Okay, homogeneous functions. Let's see how do we deal with this family of functions, homogeneous functions. If a differential equation in this form, dy over dx equals little f of xy, and it's homogeneous, then we just use another variable, because if it's homogeneous, that's a ratio of y to x or x to y, okay? And we can make another variable to represent the ratio. So we will have y equals to x multiplied by scalar. So y and x differ in the scalar. So that's the key part. Then dy dx equals to v plus x times dv dx, right? Differentiate. Then we can substitute dy dx. We can substitute this with v plus x dv dx, because that's dy dx, right? Dy dx is v plus, right? We'll differentiate this in terms of x simultaneously, right? In implicit differentiation. Implicit differentiation. Then we can change this one to be dy dx is this equals to f of v, right? We use v to substitute y over x. And we can rewrite this as x times dv dx equals to f, capital letter f of v, capital letter, so another function in terms of v minus v. Again, so this side, we have x dx, we have v dv, we have v term is dv. We can separate them, so can be separated as 1 over f of v minus v dv and 1 over x dx. And we know how to deal with the rest, right? So the key part is to make a homogeneous equations a separable equations. Let's just go back. Anyone has any question? David.
Yeah, so since you need to just get it in like the form of one variable, I guess, like y over x, f of y over x, or homogeneous, could you have f of x over y instead?
I'm sorry?
Could, like, how it says another way of saying this is that we can write f of x comma y equals f of y over x. Could you instead have f of x over y?
Of course, right? Of course, what is x over y? X over y is just y over x raised by -1.
I see. So as long as it's just a ratio.
Right, right. The key part is the ratio, right? So let's look at this. So y equals to v times x. Well, that's x equals to y times 1 over v, right? Good question. Okay, anybody else has any question? Yeah, you read as homogeneous. In mathematics, we read as homogeneous. It's okay, homogeneous. All right, so if it's a homogeneous function, we can do something. We can use substitution method. Then in the end, we use substitution to represent the ratio of those two variables. That's the key part. We use a variable, another variable, to represent the ratio of the two variables. Then we take then we differentiate, right? The process is differentiate, then we get this. Then we plug back in to the homogeneous function. Somehow we can make a separable equations. And then we know how to deal with separable equations. Okay, let's see an example. We have 2xy dy dx equals to 2x squared plus 5y squared. Well, let's divide by 2xy on both sides. So dy dxy equals to 2x squared plus 5y squared divided by 2xy, which is a function in terms of x and y. To have this right form now. So as you can see, this looks like something we called rational functions. If it's one variable, we use called rational functions, right? We always have the ratio. Anyway, but those are two variables. So we can check to see if this is homogeneous. You know, we see denominator, we see x and y appears in the numerator, in the denominator. You know, we have the sense to know it's a homogeneous function. Or we can check, we have to convince ourselves and others. So we plug in tx for x, plug in ty for y. Then we see t squared is common factor of numerator and denominator, cancel out. So proved it's homogeneous function. So now we use the method, we use a v, a nu, to represent the ratio y to x. Well, we can rewrite. We rewrite this function as this. Right? We're thinking this, we're going to use another variable to substitute y over x. So if we do that, we factor out x squared, or we cannot factor out x squared. Okay, X over Y is 1 over V. Then 5 over 2. Y over X is V. 5 over 2V. So get this 1 over V plus 5 over 2V. Gregory, question?
Yes, Professor, you're disconnected again.
Oh, whoa, what's going on? What's going on?
Objectives.
I did.
Okay.
I never had this problem.
Yeah. I need help, but I'll look into it later.
Huh?
I don't know what it could be.
Okay, thank you, though. Sorry, guys, I don't know what's going on with this. I never had this problem. Okay, I'm sorry. I don't know what's going on, and I never had this problem before. I guess I'm going to have this problem now. I use files from Verizon. Supposed to be very strong. Am I okay to you now, guys?
Yep, all good.
Yes, yes.
Okay. Sorry, I have no idea what's going on. All right, so now, so we have this dy dl. Let me start from here. Right, so we checked the homogeneous function, and we want to write this. So this is a step, right? We want to write this way. We want to represent the variable with y over x, because we're going to use v to substitute y over x. So we change this one to be this. So 2x squared plus 5y squared over 2xy now becomes x over y plus 5 over 2 y over x. So make sure you do this calculation, right? Make sure you do this calculation for yourself. This is just algebra. Everyone can do it. And then we use this one. So once we're able to write this, then we let y equals this new x or vx, right? So we just have to differentiate it once. Just try to memorize this. You don't have to every time to differentiate this, right? So implicit differentiation, dy dx, you get a v plus x dv dx. Then, so this side is dy dx. The other side is this. From here, dy dx equals this. So x over y is 1 over v. Y over x is just v. So dy dx equals to 1 over v plus 5 over 2v. And we write it because we know if it's a homogeneous equation, somehow we do this substitution, we get separable equations. With the separable equations, we know how to solve, right? We integrate both sides, and you know the rest. Okay. Anyone has any questions for this? Okay, let's see. Right, once we finish, of course, we substitute back the variable into y over x. Let's see this example. We have x squared dy dx equals to x squared plus xy plus y squared. Right, we divide by x squared on both sides. And we think, okay, that's probably a homogeneous function. So we divide by x squared. We try, oh, actually this one is even easier. So we divide by x squared divided by x squared equals 1, xy divided by x squared, that's y over x, y squared divided by x squared, that's y over x squared. So right away, we see 1 plus v squared, right? So dy dx equals this. As y equals vx, again, dy dx equals this. So dy dx equals to 1 plus v squared. Right, separable, we separate them, we get a separable equation. The rest is just use a separable, solve separable equations. All right, anyone has any question? All right, now let's go to these exact differential equations, which Ryan has taught us in the very beginning. Okay, so as Ryan mentioned, if we have a differential equation of such form, a function of xy, another function of xy, dy dx, well, look at this. If we move this one to the other side, right, we get some function of in terms of xy. And if we multiply dx on both sides, so we would get some function of xy dy and equals to another function of xy dx, right? And so this looks like differentiate some function in terms of x. Okay. If we think of y as a function of x, so we use chain rule for the right-hand side. For the right-hand side, what do we get? So we differentiate this. Now, two students, you are taking vector calculus now, Cal 3, so the partial differentiation involved. Because we're taking derivatives of vector valued functions. How do we do that? We take derivative of in terms of one variable at a time. So we use this notation to indicate, okay, we're taking derivatives of such function in terms of x. So this is called partial f, partial x. What is f with a footnote of x? Then plus partial derivative with y. Because this is taking derivative in terms of x, so we have dx over dx, or dx over dx is just 1. So we don't bother to write it. So that's why f just with footnote of x. But taking derivative with y, in terms of y, we attach with dy dx. Because that's dy over dx. Here it's just dx over dx. So that's why it doesn't show. So the partial derivatives. Partial derivatives. All right. So if we think that way, so that means this m of xy, n of xy, dy dx, we're thinking as this. So m of xy, just the function just the partial f in terms of x. And this n of xy is just partial derivative of the function in terms of y. Okay, let me know, Suzanne and Zihao, if you have any question about this. All right. So f with footnote x is exactly same as this. Okay, two different notations means the same thing. So those two notations means the same thing. So we're treating m of xy as a partial f, partial x, n of xy as a partial f, partial y. Okay, partial f, partial y, exactly same as f with footnote of y. You haven't studied this yet, right? So let's see if this makes sense. Okay, when you deal with two variables or even three variables, it's different from a single variable. Single variable, let's see, little f, f of x, right? It's just df dx. Because you only have to consider the rate of change of the function in terms of one variable. But now you have to consider rate of change with different variables. You have to consider, you have some problem of joining the class. Oh, I see. Let me see. Okay. Now you have two variables, but you have to consider the rate of change of the function in terms of x, rate of change of the function in terms of y. So how do you consider that? You can only consider one at a time. And in mathematics, we call partial derivatives. So rate of change of the function in terms of x only. So we're treating y as constant. Because we don't consider the change of f in terms of y yet. We only consider rate of change of f in terms of x. We're treating all other variables as constant. Same thing for this, right? We only consider the function, the rate of change of the function in terms of y. We're treating other variables as constant. It's called partial derivatives. All right, enough of that. So remember level sets, right? If a function we set to equal to some constant, it's a level set, right? So then in this case, so if that's the case, if we have equation as such, and we can consider as such, of course the equation has to satisfy this, right? Then we consider the solution as a level set of such function, as a general solution. Let's see an example. And of course, we're treating this equal to, so this equation already equals to 0, equals to 0. Why? Because when we take a derivative of this, what's the derivative of a constant? Derivative of c is 0. Derivative of this is this. Derivative of c is 0. All right. So if this is the equation we started with, what we are given, so the solution, a general solution, is a level set of such function. Okay, so you could, so equation this way is the same as equation this way, right? multiply dx. So we get m dx n dy equals 0. So let's see this. How do we know if m is partial derivative in terms of x and n is partial derivatives in terms of y for this function of x and y? Second, if we know this is true for some function, how do we find that function? This we call potential function, f. Because we have a partial derivative, we want to find the potential function. If we can find the potential function, satisfy m to be partial x, n to be partial y, then the level set of this is a general solution to this or this. So notice this function has a continuous second partial derivatives, which means, remember, in Euclidean geometry, the second partials, the mixed second partials have to equal to each other, right? Which means f, partial square f, partial x, partial y, the same as partial square f, partial y, partial x. The second derivative, the mixed partials have to be the same. And we use this property to find the potential function f with the given m and the given n. So m is partial in terms of partial f, partial x, n is partial f, partial y. So then, if we take a derivative of partial, if we take a derivative in terms of partial m, partial y, that has to be the mixed partials fx, y, right? So we take a partial derivative, we take a derivative on both sides in terms of y. So that's partial m, partial y is equal to partial square f, partial x, partial y. And if we take derivative of n in terms of y, in terms of x, so this will be f, yx mixed partials. This will be partial n, partial x. That have to be the second mixed partials. And those two mixed partials have to equal each other, equal to each other in Euclidean geometry. So far, we're working with Euclidean geometry. There's no curvature involved, so the partials are the same. So that means partial m, partial y have to be the same as partial n, partial x. So we use this property to find potential function f, all right? We use this property to find the potential function f. But if those two are not equal to each other, that means this not equal to a derivative of a potential function, right? Then we won't be able to go further. Okay, let's see this theorem. Suppose m and n have continuous partial derivatives in the open rectangle. X goes from A to B, Y goes from C to D. Then the differential equation of such is exact if and only if goes both directions. If this is true, this is true. If this is true, this is also true. If and only if, both directions. So this, if it is exact, if and only if this. So this is a partial m, partial y is the same as m with a little y, with footnote y. Okay, so this m with footnote y is exactly this partial m partial y. And this full node n, this n with full node of x, in this case, in this context, is partial n partial x. So take the rate of change of m in terms of y, the rate of change of n in terms of x. Okay, we take a derivative of m function in terms of y only. We take derivatives of function n in terms of x only. We're treating y as constant, we're treating x as constant. Okay, let's see an example. We have this function in terms of xy dx, with this function in terms of xy dy equals to 0 in the form of the previous equation. So this is the m of xy, this is the n of x and y. So m of xy equals this, n of xy equals this. Right? Any method we use, we want to identify to the formula. Okay. Now let's take a derivative. Let's do partial m partial y. Let's do partial m partial y. Because the partial m is a potential function, is a derivative partial potential function in terms of x. So we want to get mixed partials. So we do partial m partial y. It's same as partial square f partial x partial y. Right? Because this is partial f, capital letter F, partial f, partial x. So when we take a derivative in terms of y, we have partial square f, partial x, partial y. Mixed partials. So partial m, partial y. So x cubed, because we're taking derivative in terms of y, we're treating x as a constant. What's the derivative of constant? 0. We're taking derivative in terms of y, we're treating x as a constant, so that's y over a constant. Right? So 1 over x is just a number in terms of y. So derivative of 1 over xy, just 1 over x. We're taking derivative partial n partial x, right? Then y squared, we're treating it as constant. So derivative becomes 0. Then derivative of ln x in terms of x is 1 over x. Bingo, right? Mixed partials equal to each other. That's a guarantee. So if this is true, the guarantee comes. The potential function, capital letter F of xy, can be found. If the mixed partials are equal to each other, the potential function can be found. Now, so how do we find it? Partial f partial x is m. Remember, m equals this, x cubed plus y over x. That's partial f partial x. Partial f partial y is n. That's y squared plus ln x. So we integrate. So choose either equation and integrate with respect to appropriate variable, right? So potential function of x, y, if we integrate partial f partial x, right, what do we get? Remember, as Ryan mentioned before, when we take a derivative of partial f partial x, we're treating y as constant, right? So that's why when we restore the potential function, when we integrate partial f partial x, what's partial f partial x? That's partial f partial x. We integrate in terms of x, dx. So that's x raised by 4 divided by 4. That's y ln nx. Then we have to add a constant. What is a constant? When we take a derivative, what's constant in terms of partial f, partial x? That's a function of y. Because when we take a derivative of f in terms of x, we're treating y as constant. So when we integrate partial f, partial x, we have to restore the function y because we're treating it as constant. So the constant in this case is function of y. Anyone has any question? Especially for Suzanne and Zihao. All right, good. So partial f, partial y is just, right, if you take a derivative of this, partial f, partial y, x term is constant. So derivative of this in y direction becomes 0. And the derivative of in y direction of this just ln x. Derivative of g of y just g prime of y. And we know from the very beginning, n is partial f, partial y. So n is partial f, partial y. What is n? Y squared plus ln x. So both are partial f, partial y. So one way we found from partial f, partial x, by integrating partial f, partial x, we get partial f, partial y to be this. Another way, we're given n as partial f, partial y as this. So those two must equal to each other. ln x on the left-hand side, ln x on the right-hand side cancel out. So g prime of y equals y squared. Integrate this, we get a 1/3 of y cubed plus a true constant. So now we plug this g of y back into this function, potential function. So get our potential function. So our potential function is just quarter of x raised by 4 plus y ln x plus 1/3 of y cubed plus a constant. And remember we said that's a solution, right? We're treating this. So the solution is just a level set, a such function, this potential function. So what do we do? So our general solution in the end, just this equals to a constant. Don't get confused with this C, okay? C just represents a constant. That's it. That's it. And you may choose, so this example choose to work with partial f, partial x. For you, I would suggest you to choose partial f, partial y to work with to see if you get the exact same solution, all right? You choose partial f, partial y to work. Well, what's partial f, partial y? Partial f, partial y is this, but you integrate this. You integrate this in terms of y. Then you add a function of x, right? Then you take a derivative of that in terms of x. They have to equal to m of xy. So that's another way of solving this. Choose to work to integrate partial f, partial y. Any questions? All right. I think everybody's good. Now let's try this example. We see m dy minus n dx equals to 0. Perfect form, right? Perfect form. Well, let's check to see if it's exact. If it's exact, the mixed partials have to equal each other. So m is, m is the one before dx, right? M is the one before dx. N is the one before dy. So m is this. N is this. Because m is partial f partial x, right? So that's why this is m. N is partial f partial y. That's why this is n. So we differentiate partial m partial y, right? So we differentiate function m in terms of y. What was it again? Negative 2, 1 plus y. Function n, we're taking partial derivatives with x, because this is partial f partial y. So partial n partial x is a mixed partials. So if we differentiate this in terms of x, we get a positive 2 times 1 plus x. And in this case, what happened? The mixed partials not agree with each other. Not agree with each other. So what do we do with this? So we cannot restore. We cannot go this way. Right? In this case, in this example, we see the mixed partials equal to each other. If they equal to each other, we could go through this way. We integrate one of the mixed partials in terms of the variable, right? Then the other variable, the function in terms of other variable was treated as constant, so we restore it. Then we take a derivative in terms of this variable, y, in this case. Then the mixed part, then they have to agree with each other, right? We set them to equal. So we solve for the function in terms of the other variable, we treat it as constant. Then we get a solution as a level set of the potential function we found, if the mixed partials are equal to each other, right? Let's see this case. In this case, the mixed partials are not equal to each other. So what do we do? So the equation is not exact. So we have to find another method. We'll find another method. So in this case, actually, we can separate the variables, because this is just involved with x, this just involved with y. So we write as 1 plus x squared dy, 1 plus y squared dx, and we want to put the y in one side and the x on one side. So what do? We divide by 1 plus x squared, 1 plus y squared on both sides. Now we are having y together, we are having x together, separable equations. So the rest, you can do it, right? We integrate this equation simultaneously on both sides. And this is just 1 plus y raised by negative 2. We use power rule. We get this. Power rule, we get this. Simplify the constants. Right. We could just flip this plus a constant. Okay. So 1 plus y, we simplify, in the end, we get things like this. Then with y is equals to this minus 1. So that's for the mixed partials not equaling to each other. We use separable method. Let's see this one, reducible second order equations. So second order equation has this form. Such potential function takes 4 variables, right? X and y, first derivative, second derivative, and it equals to 0. For example, this one, I think Christian showed one example similar to this. So for example, xy to the second power to the second derivative plus y to the first derivative equals 4x, and y double prime equals to 2y times y prime to the third. So those two equations involve second order differential equations. Involves the second order derivatives, so it's called a second order differential equations. If either y, the dependent variable, or x, the dependent variable or the independent variable are missing from the second order equation, then the second order equation can be reduced to a first order equation by letting a variable equals to the first order of differentiation. So such is a function of x and y. Let's see an example. So we want to solve this second order differential equation, and we want to reduce it to a first order differential equation. So what do? We just use a variable, right? Actually, not a variable, a single variable function for y prime. Excuse me. So we take a derivative of this, then we get a second derivative, right? So p prime is the second derivative of y. Then we can change this original equation into a new equation. That would be first order equation, first order differential equations, right? So y double prime is just p prime, y prime is just p. So we just have to solve these first order equations, first order differential equations. So how do we solve this? We see this can be written, we develop x for all the terms. This can be written as p prime plus 1 over x, p of x equals to 4. Wow, that's in the p of x, q of x form. Right? So that's in the p of x and the q of x form. We call this p, right? We used to call this p. So I guess this is a typo. This is not supposed to use r. This is a typo. Okay, this should be p. It should be p. We can use integrating. We want to find the integrating method, right? So the integrating factor as defined as e to the integrating p of x. So we integrate 1 over x. Or integration of 1 over x, just ln x. Or e to the ln x, just x. So I have found our integrating factor. Multiply every term by integrating factor in the first order differential equation. And then we know the left hand side is the differentiation of x times the integrating factor. That equals to 4x. We integrate this, we get xp of x. Integrate 4x, get 2x squared plus some constant. So we have solved the p of x. We have solved the p of x. Now we can substitute this back in p. So p equals to dy over dx. Right, so dy dx equals to this, which is 2x plus a constant divided by x. Excuse me. So we integrate both sides. Right? We integrate both sides. We integrate dy dx, we get a y. We integrate 2x, we get x squared. We integrated 1 over x, c1, or just c1 ln x, then plus another constant. So we have this general solution. Anyone has any question? All right, let's see the second example, which is y double prime equals to 2y times y prime raised by cube. Again, we let a function of x equals to y prime, so we rewrite the given equation as, so y double prime equals to first derivative of this, we define the function we defined, and it equals dp over dx. Well, y by chain rule, this is dp over dy, dy over dx. Well, what's dy dx? We define as p, so that just equals p times dp dy. So y double prime is p times dp dy. Then 2y times p cube. Again, we see this, we make this form separable. So on the left hand side, we have 1 over p squared dp. What is dp over p squared? The right hand side, we have 2y dy. We have separable differential equation. We integrate both sides. Left hand side, we get negative 1 over p plus a constant. Right hand side, we get y squared plus a constant. And we want to solve for p. Okay. So we isolate negative 1 over p. Then we just flip it over. So p equals 1 over negative y squared minus some constant. Now we substitute back p as a y prime or dy dx. So dy dx equals to this. Again, we see this is separable, right? So we have dy times this, or this times dy, or negative 1 times dx. We integrate both sides. Well, y cubed divided by 3 plus some constant multiplied by y plus some constants. Then integrate negative 1, that's the negative x plus some constant. Combine the constant, we get x equals to such. general solution. C3, C6, just representing some constant numbers. Anyone has any question? That's it for today. So we have learned substitution method for homogeneous functions and for function in a special form. Function in a special form. Right. Function in a special form, we can use the substitution method. And the homogeneous functions, we use a variable to represent the ratio of the two variables. Right. We make a substitution. A variable equals the ratio of the two variables. Then make a separable variables equations. Then we solve from there. These examples. Exact differential equations. We have m a function multiplied by dx. We have another function in terms of xy multiplied by dy. We're treating the one with the dx as a partial derivative of a potential function in terms of x. So if the potential function is capital letter F, m will be partial f, partial x, n will be partial n, partial y. Then we have two situations. One situation is the mixed partials are equal to each other. Mixed partials are equal to each other, which means the function survive in Euclidean geometry. And then, if this is true, the mixed partials are equal to each other, then the solution would be this is just our showing. The solution is a level set of the potential function. Or if the mixed partials not equal to each other, we can use the separable method. In this case, the mixed partials are not equal to each other, so we could use the separable equations to solve it. And reduce second order equation. So this shows us we can always reduce, if we have a higher order equations and it involves all the lower level differentiation, we can always reduce by substitute the highest one with a variable. Then once we solve for that, we plug back in the equation. Then we deal with the second one, highest one. Then we deal, keeps going. But this just shows second order equations. We use reducing method. Okay, we use one variable or one function to represent the differential, the first level, the highest level. No, let a variable to represent the differential, differentiation of differential dy. Okay, let's put this way, dy dx. right? Then each time we can reduce, but this is only second order, so you only need to do twice. We let a function to represent the first level of differentiation. Once we get an answer for that, we reduce. Once we get an answer for that, so the second order equation will be reduced to first order equation, first order differential equation. Then we can solve. Okay, for higher level, we can just mimic this reducing method. Okay, that's all I have to say. Anyone has any questions? Oh, I see some people already quit. All right, if you have no questions, today's class is long, all right? There are 3 kinds of equations we're dealing with. And there are also different methods to apply to it. So I don't have anything else to talk about. And if you don't have questions, you are free bird. You can go ahead to try your homework. Or, okay, before you try your homework, a suggestion is this. This is when I was a student. When I was a student, I make sure, you know, I indeed understand the example. So I would do the example myself. I would do every example myself on my own. Then I compare to the solution already there. You know, once I feel comfortable with that, I start to do my homework. All right, have a good night, and I'll see you next Tuesday, okay?
All right, good night, Professor.
Thank you, Professor. Have a good night. See you next Tuesday.
Good night. Good night. See you Tuesday. Good night. Good night, everyone. Have a good weekend. Okay, I'm going to stop